Good morning, everybody. So it's already the last day of our school, and today's topic is now mostly about polaritonic chemistry. This morning is slightly special because so the first part will be my lecture with exercise, but then the lecture sort of continues in a more public seminar. It will be a little bit repetitive because if there are more people coming, of course, I need to motivate what I'm actually talking about, and you already know, but you will see. And the main setup of this polaritonic chemistry, or one of the main questions this morning I would like to illustrate. I cannot fully solve it, but hopefully get closer to a solution, is this question of local versus collective mechanisms that appear in a cavity under strong coupling. A bit more in detail, the outline of my lecture. So first part, how we simulate molecular ensembles in a cavity. Just some, I would say, part of it is repetition, but I would like to highlight some specialities. And then we mainly look in the morning on vibrational strong coupling, not exclusively. And in the afternoon, Johannes Flick will then talk about electronic strong coupling. The goal of this morning is a bit to give you a bit the fundamentals, but also then try to illustrate some properties on very simple toy models, or more or less simple toy models, aiming for a collective insight. So usually having a lot of molecules, and of course having a lot of molecules makes computations a priori difficult. We will talk a bit about the relevance of non-perturbative aspects. Also very briefly what temperature plays in there. There are a lot of open questions in that regard, but I can illustrate some aspects that arise. And then we do that with very simple harmonic toy models in dilute gas limit. And at the end of the lecture, I want to make them a little bit more complex, add unharmonicity, and also then look at electron correlation effects, so that in the end of the morning, at least we have, I don't know, sort of a roadmap where to probably go in the future. To start with, I would like to show you some experimental results of the Ebbesen group. And this is an NMR experiment where they looked at this molecule. And this molecule here has two different conformational states. So you have a solution, both of them exist, and they are in a certain equilibrium. Now, what they then did, they tuned the cavity on resonance. You don't see all the details here with the vibrations. And they did that in an NMR, basically looked at the NMR spectrum. And what they then found is that over here, so what you see here on the x-axis, you increase the concentration of the molecules, meaning you increase the Rabi split, your collective coupling. And then suddenly at some concentration, you see this drop of this equilibrium constant. So it means you change your conformational equilibrium, and then it very roughly stays constant after this, I would call it phase-like transition. What was sort of surprising is what happens to the NMR spectrum, because what you see here is off resonance NMR, on resonance, and you see these peaks here. They look that they are on top, and what that usually is interpreted as the electronic structure didn't change in there. So if you change your electronic structure property, usually in the NMR, you would see a shift in one or the other direction. And that was very surprising. And it's still not fully understood how this all gets together. But already a little bit a hint, I will in the end come back to that. Possibly, I mean, this is an average quantities. You look at a lot of molecules. On an average, nothing changes, but probably here you get a different broadening you might change the deviations from the average in the cavity. I mean, this is not fully resolved yet, but just to give you an insight. So, and this experiment, I think, highlights two critical aspects that are not yet resolved, but I would like to talk about is, or probably more than two. So one of it is London dispersion forces seem affected because they are known to be responsible for these structural changes. So you somehow change London dispersion force, and you do that locally. I mean, you change the structure locally, but you couple collectively. So there is this collective local mystery that determines a lot of the work in chemistry. And the other thing I would like to highlight is that we get sort of a phase-like transition in this equilibrium constant. And this phase-like transition, this is not exactly where the Rabi splitting starts. So it seems to be a different mechanism, meaning if you have strong coupling, doesn't mean you get a chemical change. And this is the big question also in the experiments. I mean, often nothing, they don't see anything. And if they are lucky, they manage to change chemistry. I think there was a question.
Maybe a very naive question, but what kind of interaction are London dispersion forces? Is this?
This is electron correlation between the molecules. Okay. I will come to that in the seminar. Back to that. Other questions? Very brief repetition. You should have seen everything on this slide, but I think it's good to highlight also now from a bit more chemical perspective. So this is the, I would say, the Pauli-Wirth Hamiltonian that Ruby derived in its full glory, probably. And this is very hard to solve computationally, as you might guess or know. Now, just to highlight some still important aspects, it was told to you, but I would like to highlight again, the nice thing about this formulation is we have a ground state, so we can solve Schrödinger equation. So we don't have something completely different. So if you come whatever from a computational perspective, you did last decades quantum chemistry, you might be able to use your knowledge and extend the methods for this new setup. So this is very powerful. We don't do some perturbation theory, but this is really, with this, we are used to the Schrödinger equation. We can work with that, or most people in the field, I would say. So just as a side remark. But as I said, this is too tricky. So throughout my lecture, I will focus to the simplified version. So this is in the length gauge and dipole approximation, the Pauli-Wirth Hamiltonian. What we have here is we have kinetic energy of the electrons, we have kinetic energy of the nucleus, we have electron-electron Coulomb, nuclear-nuclear Coulomb, electron-nuclear Coulomb, and then we have coupling to the quantized, these are the quantized photon modes that couple here, the displacement field couples to the total dipole of all your molecules in your system. So this is the total dipole operator. And you have then here basically the coupling constant between light and matter. Still, this beast is difficult because in quantum chemistry, people try to solve that or develop methods for decades to solve this aspect. Now we add the quantized photons, things doesn't get easier. Why this is, I would say, convenient for molecules is we don't have these periodic systems. And if you use this formulation in a solid, you get difficulties with this dipole operator. So that's why for solids, usually you use the velocity form. For molecules, usually the length. But doesn't mean this is the only way to do it. Then, as I said, this is still too complicated. Now we subsumed basically the bare matter aspect in here. And what you should also have seen is the Born So basically, you can do a Born-Huang partitioning of your wave function. So the total wave function of this system depends on the electronic coordinates, you have the nucleus, and you have the displacement field coordinates. And now you can regroup these coordinates in different ways. So I think IT, if I'm not wrong, showed you this partitioning. One way to do it is the so-called polaritonic energy surface partitioning, where you group the electrons and fields together, and you separate them off from the nuclear degrees of freedom. The cavity-Born-Oppenheimer partitioning does the opposite. It groups the nucleus and the displacement field coordinates together and separates off the electronic structure. So there is no approximation involved in this step. The approximation then starts afterwards. And this is also, I would say, a rough guideline. Usually this polaritonic energy surface partitioning is considered to be a good starting point if you look at electronic strong coupling. For vibrational strong coupling, one says usually it makes sense to group the nucleus and the displacement field together as a starting point. And this morning, we will live in this world because I'm mainly talking, not exclusively, but mainly talk about vibrational strong coupling. So what is the next thing? Yeah, exactly. So when you do now this cavity-Born-Oppenheimer partitioning, I think you also have seen that, but I would like to show you now a bit how the different, basically the electronic problem and the nuclear problem looks like. So the electronic problem is that you get in the cavity-Born-Oppenheimer partitioning contains your bare matter Hamiltonian, and then this is very shorthand notation. I have here an electronic x square. What is this x square? So this x square is the total electronic dipole operator weighted with lambda and the charge, but that's not so important. And you have this sum over all the electron position, you square it. So this gives you an all-to-all interaction between the electrons. And this will be very important later on. Then you have the total, or the weighted total electronic dipole times the total nuclear one. And then you have also the electrons that couple to the displacement field coordinates. Now, in this Hamiltonian, this depends on external parameters. So the nucleus and displacement fields are just parameters you enter in here. These are not operators. So the operators are the X or the electrons, basically. And so what you do is you can solve that. It gives you, in principle, potential energy surfaces. Can be very hard to solve. What is important here is it's not the bare electronic problem. The cavity changes your problem due to these terms, very simply speaking. And aside, due to the partitioning, you get now the nuclear quantum problem. So what you get here is, so you have the bare matter nuclear Hamiltonian. You get then terms that depend on basically now we have operators here on the Q and the X. These contain the nucleus. And you get then, so this enters in here, you get this equation for the nuclear displacement field quantum dynamics, and this is still very generally written. So here you have kinetic energy operators, and these are then the so-called non-adiabatic coupling elements. So what it means is that all these potential energy surfaces here, they start to talk to each other. And you can imagine solving that is very tricky. Now they start to talk to each other. And this is also a quantum problem, so this is very hard. So we need to, but now we can introduce approximations since we want to discuss vibrational. So I will add some approximations. The first thing is to say, okay, we don't care about non-adiabatic coupling elements. So here you don't have these cross terms talking. Simply speaking, you can imagine that this makes sense if your potential energy surfaces are far apart. Of course, if they are very close in energy, you need to consider that. For example, typically whatever conical intersections and so on. But that's whatever, a problem already on its own without the cavity. Now you add the cavity. Of course, there are interesting research opportunities, but I'm not going to talk about that. Today, for simplicity, I stay in the mostly in the simplest case, where I just say, I treat my nucleus and my displacement field classically. So what you get, what we will do with this classical Hamiltonian that you get, I mean, here you have the grounds in the grounds. So this is the electronic ground state energy you get from over here. And this is then just a classical Hamiltonian you get from here, all classical. I mean, you will see it later. And these you can efficiently propagate. People in chemistry do that since decades. It's called ab initio molecular dynamics. But to do that, we need to solve the modified electronic structure problem.
The level of the equations on the left, the photons are classical coordinates, just like the nuclei.
I mean, here it's really just a parameter. In that sense, classical, but as I said, you don't. So if you solve that and that together, it's a you don't have any classical whatever approximations in there. Yeah. It's just a parameter. You get this. Yeah, it's a way to partition your problem. I see it at least that way. And the way to proceed for the addressed electronic problem is I make a Slater determinant ansatz. So I know electrons are indistinguishable particles, and I enforce the Pauli principle by a Slater determinant ansatz, as people do in Hartree-Fock. So it's not, how should I say, this is sort of, I would say, the most natural or naive approach to approach the electronic problem to do that. Of course, this Slater determinant is a restricted ansatz. It doesn't give you the correlations, for example. I will come to that. And what we need to keep in mind, I will not really go into detail, is that the electrons also have spins. So we talk about spin orbitals. So basically, if the two electrons have different spins, they are distinguishable. So you need to account for that, but that's more a technicality. If you then use this ansatz and for the wave function, and you write down the Hartree-Fock energy expression, so here you see, again, you have the electronic kinetic energy, you have the standard Coulomb interactions, then you have the sum over all the electrons, so the dipole operator squared, you have dipole operator times, this is now a parameter, x of the nuclei, and here you have again the dipole with a parameter. And you get these terms out of it. What do we see here? We have so-called one electron integrals. This is the yellow line. I will come to that. And then you have different types of two electron integrals. And this one electron integrals, this, I call it HM. I didn't write down what it means here, but you can imagine, for example, the kinetic energy only depends on the ith coordinate. This goes in here, or this term depends on one electron goes in here, but you see two electrons, this will go in here. And then from here, you get also one electron contributions that are subsumed in that term. Now, okay, now I continue. Then you get the standard Coulomb Hartree term, and you get also the Coulomb exchange term. So this is standard, you get always in Hartree-Fock. What you now newly get is from this X square here, this introduces new 2-electron operators, you get so-called dipole self-energy Hartree term. You see here I have orbital I and JJ, and here in the exchange I have IJ, so these are cross terms. Now, very, very roughly speaking, you can think of on a very small scale, spatial scale in your system, kinetic energy dominates, otherwise you get a Coulomb catastrophe. Then on, I would say, an intermediate scale, whatever that means now, but I would say mostly probably molecular structures, they will be determined by the Coulomb energy. So this looks like normal molecules probably, or almost. And then if you go further out on larger distances, you have a different scaling because this scales with the distance, very roughly speaking. Then these terms might start to play a role. And this is a bit what then brings in eventually this collectivity aspect, I think, into polaritonic chemistry, which is hard to handle computationally. As I told you, I want to show you some more or less illustrative examples. And to make our life simpler, I impose, this is a bit ad hoc, a dilute gas assumption. So I say my molecules are very far apart. In that case, I don't care about the molecular internal structure. I just want to model the intermolecular interactions. And if I take them very far apart, the electronic structure I consider to not overlap. So the non-overlapping aspect kills me the exchange terms. And then if it's far apart, also the Coulomb Hartree you can neglect. And the only thing you cannot neglect in this extreme case, it's artificial, is this dipole self-energy Hartree term. And we will next look a bit what this can do or cannot do. And so we continue with some, I would say, toy models, but you get some collective insights and not just for a single molecule. And what you end up with, I would say, we will continue basically by assuming we have molecules that only possess one electron. So I really don't care about local Coulomb interactions between electrons because I have just one of them. And for the intermolecular interactions, I keep this dipole self energy Hartree interaction. And what I end up with is Hartree equation. I call it in the dilute gas limit. It looks like this. And this is relatively simple to solve because you don't, or should I say, you just need to iterative. I mean, you have here this n now is the number of molecules because each n only has, each molecule has only one electron, and I can self-consistently solve it until convergence. And what is important, I have n of these equations, of course, but they are coupled here by the total dipole. So I need to say they talk to each other. And this talking to each other, this is important. And I think we believe it's the origin of a lot of effects you see eventually in the experiment. Okay, to set this, what did I want to do? Yeah, just this is the cavity Hartree problem of the electronic structure. And I told you we want to talk about also the nucleus. So this is then the corresponding classical Hamiltonian that describes my nuclear dynamics in the electronic ground state. So if I solve this problem, I get here these contributions from up here eventually, and I can then propagate my nucleus, and so on. And this is what we will do eventually in an exercise as well. And so what you can define from that setup is you can, or basically from here is you get classical equations of motions. So this is the mass of the respective nucleus. You have the nuclear position, or how you say, twicely differentiated with time. And you get then all these contributions here. And what I added is also a thermal bath now. So this is, if you're probably from, I don't know, chemistry, this looks very familiar, or this is like classical or ab initio classical molecular dynamics with a thermal bath. You just add some Langevin thermal noise. So this is a random noise term that you add on top. You need to add also some friction term. Otherwise, you just pump energy in your system. So you need also a dissipation path. And this is very standard to do. People propagate that in time. And if you then look at this, I mean, you propagate your system in time, and then you look at the time average, you say your system is ergodic. And then you say, okay, what I get out from this simulation is a thermal equilibrium behavior of my chemical ensemble. Of course, there are some subtleties in practice and so on, but this we don't go too much into detail. And of course, for vibrational strong coupling, temperature plays a role. So it doesn't make much sense, I would say, to not add, to look, I mean, I'm sure you can come up with some meaningful question, but to get a generic understanding how your chemical system behaves, I think you need to add this temperature. I didn't say that, just a second. Almost all experiments in polaritronic chemistry are done at room temperature. So we cannot really neglect it. And that's also from a chemical point of view why also in the meantime, some industrial partners, they are interested in this because they say, okay, most of the chemical interesting chemistry is done at room temperature. And if we can change it now at room temperature and not whatever at ultra cold temperature, this can be interesting. But you cannot neglect the temp, or you should not neglect temperature. There was a question.
Are you after ground state properties in this case? So in the sense that you are interested
electronic ground state, yes. So what it means, electronic ground. So this is, as I said, we say we are in the adiabatic limit, and then I say my first electronic excitation is much higher lying than what you can populate at room temperature. So I don't care about that, at least in this picture. Of course, you can create a setup where you care, and then you basically evolve your nucleus or displacement field on this electronic ground state surface in time. That's a simple way to do, and it's very common to do that. Of course, depending on your molecular system, this is probably a very bad approximation, and but then things get complicated. Now, also for the exercise and to hopefully develop a little bit of an intuitive understanding for you, we make things even more simple now. So the simplest thing I can think of is a harmonic system. And so what we have here is what we look at in the following is basically we have we can have multiple nuclei, doesn't have to be one. Then we have one quantized electron per molecule, but just only one. It's an effective electron. So the charge, whatever there is, probably if you want to have a neutral, this electron needs to have the charge of all the nuclei together. This is very ad hoc. And we couple it to only one cavity mode. in the following. So this alpha here, in that the alpha sum is gone, so we look just at one effective mode. Now, if we say this is all harmonically interacting, it's a very simple problem, but it's a collective problem. So the cavity-Hartree equations that I showed you before can written the following way. You see here, you have this is bare matter, you have this harmonic coupling. So you have here, and you have here multiple electrons that nucleus. That's why it's this sum. So why do we have more than one nuclei? We want to look at vibrations. And if you have one nuclei, then you have an atom. So you need more than one nuclei. And then from the cavity, you have this I showed you before. You get from the cavity-Hartree equation, you get this all-to-all electron interactions, and the details do not matter so much. But this problem, if you look at this, I mean, these are many of these equations coupled, but what it is that you converge to the ground state, this is just our coupled harmonic oscillators. And you can shift them around and so on. The details do not matter. There are some details written. I think probably you can also write it more compact, to be honest. But what you can basically do is you can shift them around and you solve for this case, your collective electronic problem analytically. And that's, of course, very convenient if you want to propagate your nuclear dynamics, if you have your electronic structure analytically solved. The details do not matter. It's, as I said, important. What we need in that sense, what you see here, you have this, so the expectation value of your position implicitly appears here, and we can then write this. So this is in the ground state, this is this position. You can express it. You get some sort of self-consistent relation for this position that depends on all the other positions again, but this you can solve. Here you can reformulate it a bit, and you get sort of an intuitive interpretation. So the expected position of the ith electron is basically in the center of all the nuclear charges, simply speaking, and it's basically, how should you say, translated from the center of charge by the transverse electric field. And the transverse electric field, this comes from the cavity. But this, in that sense, it's sort of intuitive, but you get it out analytically, and you will see simple expressions for that that we can use for the classical equations of motion. So this is how do you usually, so what we want to do is we want to propagate the nucleus. And what you usually do is you apply Hellman-Feynman theorem. So you, in principle, you calculate the force of your expected energy, and you then just Hellman-Feynman tells you that you can take in this derivative operator inside. You can do the calculations. You can use what you have derived from the analytic and electronic structure, and what you end up with has a relatively simple form. And the important part is, because we have solved the electronic structure, you don't see it, I think, very well here, is that the electrons do not appear. So what you have here is the force on the ith nuclei will then just depend on all the other nuclear positions and q coordinates. And you don't need to calculate anything, you just need to propagate these equations. And that makes it so fast that we can do an exercise afterwards that you can actually propagate something. Some things probably to highlight a bit is what is sort of interesting from this model. You don't get coupling of neutral atoms. Is this correct? Yeah. So if you have an atom, which is sort of, it will not couple, it will completely decouple. So you need a molecule in that case that you couple. Otherwise, you don't have vibrations. But you don't. This is not obvious that you get that out of the equations. It's kind of a sanity check. You say, okay, that must be the case. But if you do the calculations, or if you, for example, say, I do this calculation, I make a sort of a smart approximation. Since you don't know, you can actually analytically solve it. As soon as you introduce an approximation, such effects are violated. That's also something probably to tell you. As soon as you start to make whatever perturbative arguments, you need to be very careful that you not run into such consistency issues.
No thermal path for Large term.
Yeah, this is not written here, but it will be added to the simulation. We only do with large above. It makes. I mean, if you don't do that, your initial conditions start to matter a lot, and I think you don't want to do that necessarily, I would say. But before we go to the exercise, I still would like to discuss a bit a special case and what we learn from the analytics. Again, the math does not matter so much, but I would like to introduce this linear harmonic CO2 molecule in one dimension. But this very simple system captures, so this is now briefly without the cavity, just this captures relevant physical aspects. So if you write down just the harmonic nuclear, or you can write down the harmonic nuclear dynamic problem of this simple system, you can do normal mode transformations. And what you find is you have a translational normal mode. You find a symmetric mode. Basically, you can imagine that the O atoms move symmetric, and you have an asymmetric mode that you find where basically the carbon and the oxygens move in one, yeah, I don't know. So I think next slide, here, it's more clear. So here you have the different type of movements. And they are also important, as we will see, and this was a little bit sort of surprising when we did this calculation. So what I now did is, before was just the molecule, and now I put it in the cavity. And what we then noticed is, so this is now the equations of motion for the transverse mode. It stays, so there is no force acting. So there is no translational force, so not transverse, translational. So the symmetric mode doesn't couple to the cavity. And only the asymmetric couples to the cavity. And now if you ask a chemist, he would say, oh, that's obvious. Because the asymmetric mode, if it induces a dipole moment, and this then, for example, gives you an IR spectrum. Now, the usual argument, I would say, okay, it's not that obvious because the usual argument is a perturbative one. If you look at if the symmetric or asymmetric couples to an IR spectrum, you use perturbation theory. But what we just did is we solved non-perturbatively the problem in the cavity. So a priori, I would have said, okay, all this feedback effect, probably I still get something that enters here. And this is a bit, I would say, the miracle of our harmonic model. I would expect as soon as you have more realistic molecules, so any unharmonicity in your system, that here the cavity should also appear. Probably the effect is very small. But just to keep in mind. And again, as soon as you introduce approximations on our electronic structure problem, you don't get that. So what I want to say is approximations on the electronic structure level can cause all sorts of spurious effects. Of course, we need to do them some sort of way, but this is what the model shows. Be careful. Then, yeah, so this is basically for a single molecule. You can also write the equations of motions, basically collective by summing over all the corresponding modes. This is, I think, at least for the matter part, I feel not so important, since my focus is I want to know what happens to a single molecule within this ensemble. But some aspects we get is, so what I wrote here down is the equation of motion for the displacement field. And what you notice is you get a renormalization of the cavity frequency by this gamma here. And this renormalization, do I have it here? Yeah, this is this gamma expression here. This is, it would be larger than, larger equals 0 and smaller equal 1. So you get here a redshift of the cavity mode. And what else do you get? So you get, of course, also renormalizations of the, not of course, you get, so your, how should I say, your coupling constant or dynamics of the asymmetric mode is not directly changed. So here you don't get a renormalization, but you get it collectively. What this means, to be honest, is to me, it's not entirely clear. It's just how it looks like. And now we have seen a bit, I don't know, we have looked at the CO2 molecule. We solved self-consistently in the dilute gas limit the electronic structure. We have seen some normal mode properties, what couples to the cavity, what does not couple. And what does it do now, the system? This is the question of the exercise. So I hope you have the latest version of the exercise. So it's notebook 9.
On the repos notebook 10. It's just because yesterday we had 9 and today's 10, but it's the same one.
Okay, but do you get this? Is it on the same repository?
Yeah, yeah, I think it's fine. Yes.
Okay, okay. So if you
just because we inverted with the QDFT.
Okay, because yeah, I'm still confused. Can I see what how it looks like in your?
Yeah.
Who has it up? All right.
So they have the participants, and I uploaded yesterday, but because ETA was notebook 9, I uploaded as notebook 10.
I didn't know that you uploaded, because, but this is the latest one. I hope it's. No, this is. I think you uploaded the solution. Okay, so there is an issue. I think you got the solutions uploaded, then, which is also good for you. I think so, at least. Because I thought you. Yeah, this is the solution. So what is then, because I changed it yesterday morning, I think.
But I uploaded it last night.
Yeah, but is it from the right repository then? Because I just had one.
Okay,
I guess what I guess from
but I did not resplit it. So what we were doing is we have a change here, we would split and then copy it to the participants one. Is that the issue?
Yeah, probably there is some, because what is this one? I think this, yeah, this would be the right one. I think that this is the naming.
Okay,
I think this is the, so you can overwrite it and I mean,
I'll upload this one. Just
okay. So I think there was an issue with uploading the right one. So please don't use the solution because you need to add some parts in the code, and which when if it's already there, it's I don't know how much sense it makes.
Then I'll pull again.
Yeah, that you should just pull. Is it uploaded the new?
1 second, 1 second.
Okay, just let us know. Okay, so it's.
I don't know if we changed today.
I think today is somehow shifted. I think it's till 11.
So that's mine.
So the probably just to say, so the idea of the exercise overall, or the beauty of this MD is the electronic problem is solved, so it's very efficient. So you can relatively efficient play around with the parameters and scale up the number of molecules. And usually scaling up the number of molecules on the collective strong coupling is almost impossible without HPC or something like that. So you get it's just harmonic, but you should get a bit of feeling of how such a vibrational strongly coupled ensemble behaves. And I think now you can pull again and then your solution is gone. And look at the exercises. And so there are several ones. So it's quite, I would say I assign half an hour now. And then 20 past, I mean, I will be around, I can answer questions. Then 20 past 10, we can discuss the exercise. And then I continue with my lecture till 11. Today it's a bit shifted.
Yeah.
Questions? No.
That I don't see.
When I will leave, I think at 2-ish. Yeah, no, I assign enough time.
So when is your?
Yes, I think you might have modified it. And
Can check it out.
which one? Which one?
Oh, okay. No, I will log out. We should share it. Definitely not. That would be very stupid.
Book question.
What? Okay. Yeah.
Okay. I think it's altogether 10, and then. Yeah,
You make my heart.
yeah, okay, good. I mean, just on this.
And on this integration. Please.
I'll just check with you.
Do you have any changes in the repository that you would like to keep?
I think
Yeah,
my
okay, I just
solutions
use it.
to some of these.
Or it's me to.
I mean, it's fun.
Happens when you repeat the actual
Yes.
Yes.
Under notebooks.
It should be the notebooks questions.
How about grid restore stage this
Okay,
Yes, thanks,
of course.
This. No.
Then, okay, I can check. I can check.
Stop between the two kids.
Third time's a charm. What is the study that I said yesterday? Didn't put it on the list.
Okay, then it doesn't show up. That's fine. I mean, we had an appointment yesterday.
I saw the whole thread. There's no confirmation at all. It's in.
Deal. So much.
I don't see the notebook at all.
Seems like.
Okay, so you go to workshops. And then the participants.
Yeah, now we can check it again.
Yes.
Yeah, but it changed the same file. It changed
Did you do it? Did you do it?
Now it's so now you can use bullet.
It's just
Maybe it's one of those. One, and then the other one. Anyway. You can. The bar. Yeah, there you go. Yes.
Yeah.
Set excuse for one-dimensional.
So I was wondering, because
Get the simulation. But the effect. Yeah, it's all classical. It's all classical. Now the quantumness will come back again. Don't worry.
It's not the problem. Have to prove that everyone.
It'd be nice to see it written. Then one can refer to this period. Oh, by the way, this guy.
Yeah.
but in a way that's just if you always claim that then there's
slow quantumness.
Yeah, but then there is this exploration potential.
Yes.
That's fun in a way. Yeah. True. But then the way you solve it is still through a certain equation.
Yeah. You have to
talk about external potentials, which are fully passive or unit maximums. That's it. Yeah, true. But then you know that equation, that orbital independent equation is maximum. Oh, yeah.
What I do. Okay, is this
For the outside, there's work for the inside as well. It's arbitrary. There's such a thing. I don't know what I mean. I'm just taking the analogy to the extreme, because if the outside is maximum and the inside is something else, we can
it's something else.
parts from the inside to
Yeah.
the outside. And
Yeah, but now with something complicated remaining on the inside that you can call quantum. Like,
why? Arbitrary what you put inside or outside.
whatever.
So you cannot
solve the
Maybe
I have to write it up with.
Okay.
But you cannot move.
the problem with
And the way you wrote it,
Looks like
it looks like you can.
electronic, like you said,
That's
you
a
solve
solve.
Yeah, it's only, it doesn't have to do with cavity one up. I mean, I do the cavity one Oppenheimer conditioning that I remove not separated nucleus and displacement field because I'm primarily interested in something they do. And that I can solve. In that case, the electronic problem is,
Maximum you say is linear and
means
time.
I say my system is fully harmonic. And so the matter is harmonic, and the coupling to the cavity itself is also, but that only has to get a coupled harmonic problem. And it turns out
the coupling between the electron and the matter is also
it's harmonic. It's a toy model. As soon as you, so I say basically the nuclear with all the Coulomb terms.
Okay, fine.
Instead of a Coulomb by putting harmonic. And then I also say only one effective electron in the molecule to then really look at this intermolecular properties. Of course, in reality, it's much more difficult if I cannot neglect a little bit more realistic. And in anharmonics, it's more than one electron, then all help. I mean, it's interesting and important, of course, but here it's really to get the feeling of what does it mean.
Then what you're saying actually is that only because the moment you separate system into subsystems and you solve them paired, you always get nonlinearities. So that's the trick.
Non-linearities in the harmonic equations, like you have the expectation.
I mean, essentially.
In the eigenvalue states. You showed the trick where.
No, but it's neat.
It's neat, very neat.
The way you show it.
I think you get all, so it's in that sense you don't have non-linearity. I mean, what is a bit different is that, how should I say? I'm not entirely sure if I understand the question, but usually principle, the case where I say decouples and every chemist would have said
That's obvious.
Well, no, well, I think it might be a diagonal problem. I some operator, and within that operator, you have it.
Which kernel are we supposed to be using?
Although
I don't know if there are
the
the updates.
I'm sorry.
I would say maximum equations are equations of charges rather than photons.
That one,
They're all sourced by charges.
just for exploration. I would
It's just because I don't believe in photons.
no, basically.
Because you cannot see them. You can only sense them through charges.
Totally free of what you make a small hundred. Because other people would say only see photons.
But because you have a photon hits charge. There is never a problem about charge.
If they are on the should be
Not photons. Well, unless it's an endionic. It's made of.
Okay, I can upload this. Okay. Is this the only one? The only.
That's what exists.
Yeah, there will be a seminar talk afterwards.
Maybe that's the problem.
Okay, I'll put this then in there. In
This
the
is a mixture.
Already from the beginning.
So I have just heard that you don't have the lecture slides that were also supposed to be uploaded. So he will do that. So you can soon download the lecture slides that I just showed you.
If you have the slides.
Yeah, this is interesting.
I already implemented the spinner into the system. I am not so sure how the spinner coupling will change.
Yeah, exactly. There you see it, you get this collective terms.
And then also, as you mentioned, like in the when we derive the and there we also have a new factor, and somehow we can include the classical one.
To me, it is very, very closely connected to what we do in microscopic theory, right? Where you basically have a response function, and then you say, I want to take this equation curve thing, do in a similar way. That makes very much sense.
And another thing is like just a different solid state property, or the solid state property is modified by this.
Hidden together with the support papers. Dear sir.
No, it's under slides. Yes. It's number 5. Okay, cool.
Check it's the right one. Okay, see, with the tablecloth, and we had.
The slides should be there now.
Okay, the slides should be there. You can download.
Then we had this.
Are there actually other slides missing from other lectures you had so far?
Just let it fall down. Yeah,
yes. Is this a yes? So probably I mean, what's the overview of all the slides?
But
So So we will try to fix that. At least I think you should get all the slides.
Complain because we're super active, always because it was so fun. But they're also cool. They would upload their own slides there. Never cool. Always nerdy. Responsible for doing the notebooks. I missed that. That's all right here. Number of countries.
They were, you mean that you basically by adding more molecules, you increase the coupling? Yes, yeah. That's what it is.
So
I would say that. I mean, I don't know. Yeah, so this is it was not made. It's good that you raise this aspect. This show if I have this. So you always get there are always details with square root the number of them.
I think right now, like it's all
Yes, that's what this is.
Process all of it. I mean, if it's okay for you, then you.
There are still, let's say, usually quantum operations telling out no, there is no now plenty of experiments showing that, and it goes exactly in that. Okay, so I think I hope you enjoyed the exercise, but now I think we need to briefly discuss it. I will just go briefly through if that is okay for you. And I try to highlight a bit the main aspects you probably could have seen or should have seen, or try to see, whatever. So just in the first part, bare matter, you should find a vibrational spectra that looks a bit what you just see now. And you should have noticed, so there are 3 lines. And I wrote it here. So this coarse line is the total dipole of all the molecules together. And then, of course, for the given time span of your simulation, you see it's rather noisy, despite some filters that were used to appear it a bit nicer, but we didn't discuss that. And then you get this resonance, which is located at the asymmetric, so higher active vibrational mode. Then what I could also do is in the simulation, and this is what you usually would measure in an experiment. You cannot access a single dipole basically of a single molecule in an experiment. But in the computation, we can also ask how do the local dipole fluctuate of each of the molecules. You see that it's much less noisy. You get this peak. And then what you also, when you now look at the fluctuation of the CO bond instead of the dipole, you notice there is another mode. And this is the higher inactive one. And this, yeah. That's bare matter. Then, I mean, and before you might have seen here that you get whatever temperature effect, and the more molecules you have, basically the more constant the mean is, but you get this fluctuation. So this is just basically thermal noise. Then this is, I sort of skip a bit. What you should have noticed is that at the beginning, you didn't get really a Rabi splitting when you coupled your system. And that the reason was that your cavity was detuned. So you chose your cavity frequency and your bare matter frequency to be the same, but due to the electronic structure, due to the self-consistent solution I presented you before, there you might remember we had this gamma value which renormalizes the cavity frequency. So you had to adjust for that to get something like a symmetric Rabi splitting in your simulations. That you, yeah, this is now roughly set. What you notice here is, again, the red Rabi splitting, this is what you measure in experiment, what you see. When you monitor the local dipole fluctuations, you also see this lower polariton peak locally, upper polaritonic peak locally, and then you have this peak that does not appear in the spectrum, and these are the so-called dark states. So they are, in that case, they are populated by the thermal bath, so they exist, but they are more or less on, not much changes there. It's like more or less the same peak, like there is no cavity. So they don't do, at least in this picture, a lot.
What is the difference between a total resonance and a local resonance?
So you just, so basically you calculate in one case, you sum over all the dipoles of your ensemble, and you look at these fluctuations. This is like the ensemble dipole. You don't know what is in there, you just look at the ensemble. And that's what you measure in experiment. You always have a lot of molecules and you measure them together. And then, of course, in computation, I can also ask how do the single dipole of a molecule fluctuate? And this is then more rich, but you don't, collectively, you don't see these vibrations.
So it's technically the total dipole the collective coordinate and the local dipole the local coordinate.
Yes, I think you can say that, yes. Yes.
So the green curve, the Rabi splitting has symmetric amplitudes for red and blue detuned, while in the red curve you have slightly different intensity values. Do you understand that?
I did not look at that, to be honest. But usually, at least in these type of simulations, let's say small changes of the intensities is not so meaningful, but probably it's a good observation. I don't know why this is the case.
Motion, we should imagine for the dark.
So the way I see it is that you have, how should I say, the molecules, they vibrate on the bare matter frequency, but they are sort of synchronized that the total dipole does not fluctuate. So that's the picture that I have, sort of. Where was I? And then, so this is now, I would say, very, I don't know if you got that far, but a very relevant observation. So, I mean, here I don't know, probably these were 20 molecules. You got a certain Rabi split for whatever coupling parameter. And now the question is, what changes if I try to get the same Rabi splitting, but with more molecules? And so if you increase the number of molecules, you should have noticed that your Rabi split also increases. So this is then called the collective strong coupling effect, and the Rabi splitting increases as the square root of the number of molecules you put in there. And then usually in the experiment to see a Rabi splitting, I mean, there is, I would say, more or less a macroscopic amount of molecules involved. How many, this is, I would say, an open question, or which is very interesting to ask. And so what it means is if you have more molecules, I reduce the lambda light matter parameter to match what I see. And when I do that, I get that. Of course, I have now more molecules, so I get sort of less noise for the given simulation time. It reduces noise. But what you then notice is, I mean, this is a logarithmic scale. And so how should I say, the big question, and this I would say, or one of the big questions in polaritonic chemistry, or I would say generally in these cavity modified materials, is how do you get locally a chemical effect? Because chemistry is a local effect. You want to whatever change a chemical reaction that happens on a molecule, or you want to change molecular properties. You don't care so much if your ensemble dipole behaves differently. And now the big question is, how can you do that? You get this collective strong coupling, this you see in the IR spectra, but what you want to change is here is the single molecule. And now you look, if you look now at these local polaritonic peaks in this logarithmic scale, if you increase the number of molecules and you keep the Rabi split fixed, that they will get smaller and smaller and smaller. And so the interpretation would be, if your n is not just whatever, I don't know, 200, it's 200 billions. So how do you change chemistry? And that's one of the big questions in the field, because if you, whatever, usually quantum optic model, they would also tell you, yeah, you get these collective effects, but if you look at the single local scale, nothing should change. So what do you see then in the experiment? And this harmonic model, this cannot answer the question, because here you see exactly this effect that you in principle don't want. And that was a bit, I would say, the important message I had from the exercise. So let me continue with the slides. These are the wrong slides. I think this is just summarized what I just said. So if in this simple system, you will basically, your local effect vanishes under collective strong coupling. And then what do the experiments see? This is active research, and brings me to a next topic a little bit. So this is still, this picture illustrate, we still are in this harmonic molecular picture that I described, that you simulated now, the vibrations. But now I don't look at vibrational properties. I want to look at electronic structural properties. So the picture changes a bit. And something that we noticed, and we were surprised because we got at the beginning very confused, and now we are very happy when we did that, is that in this simple molecular system, if you look at the electronic problem now, you can add a constant external electric field to your system. And then the system, this harmonic system, is so simple that you can either solve self-consistently your original problem plus the external electric field. So you solve H dot diagonal, like I showed you before, just for H. Or you can alternatively treat this external electric field as a perturbation using perturbation theory based on the solution we had for the H. And you then get qualitative different results. So what we looked at is for a single molecule inside the ensemble, we looked at the polarizability. So this is the polarizability of a single molecule, I call it alpha tilde of the ith molecule. Is basically you take the derivative of your electronic position operator or dipole with respect to the externally applied field. This is definition. This is always correct, independent whether you do perturbation theory or not. Before in the derivation, there was this renormalization gamma squared appearing that depends on lambda, so on the coupling, and here also the number of molecules appear. The alpha that you see, I without the tilde that you see, that would be just the bare matter polarizability without the cavity. And then you can, as I say, you can solve the full Hamiltonian, you can then calculate Hellman-Feynman, your local polarizability. And what you find in this non-perturbative manner is that it's the matter polarizability times this gamma square. If you do perturbation theory, you come basically from the energy. This is the standard expression you have. You can also solve it, and you get also alpha I times gamma square. But here you have a 1, and here you have an n. And that's, to my knowledge at least, in the field of polaritronic chemistry, the first time that you get this is just for this observable, for this specific setup. So I wouldn't say this is a generic, don't call it a generic result. But the beauty is, the first time we see that a non-perturbative observable locally under collective strong coupling corresponds to what you would get by single molecular strong coupling. So by just taking one molecule, putting in its cavity, increasing artificially your lambda parameter. And if you do that usually, and you hand in, if you do, I mean, most or many ab initio simulations, they can only do that, or probably not 1, but 2 or 3 or 4 or something, and then you're out of memory or whatever. And this is kind of the first time that we see, okay, for this observable, just increasing the lambda gives you the correct result. So, and the lambda collective is defined here. So you take your lambda and multiply by square root of n. This is this collective scaling effect. And surprisingly, this is also the same if you do perturbation theory for single molecular strong coupling by artificially increasing your lambda. But it's not the same if you do perturbation theory locally or in your ensemble. And so if you look at that, this result will tell you, if you increase n large, that you end up with the bare matter polarizability. Nothing changes in your system. However, the non-perturbative treatment tells you indeed your polarizability changes locally under collective strong coupling. And that's, it's.
So this type of coupling is in what is length gauge, right?
Yes.
And in principle, you get polaritonic modifications of your electronic coordinates as well that scale with the light matter interaction. If you do the PZB transformation between Coulomb gauge and disk gauge. Have you looked at this in this study?
So you mean what this means in velocity? Or
yeah,
what?
So a Coulomb gauge photon is not a length gauge photon. And the same is true for the electrons, right? So a length gauge electron, or the R operator, is not necessarily the same as a Coulomb gauge electron operator.
No, I think that the R operator shouldn't change. What changes is the displacement field changes. So the Q operator changes. So the definition of your field changes. But the position operator doesn't change. So what you can imagine is let's say in the velocity form, you have your Q, and this is a photon. And now if you go to the length gauge, now your photon can be separated in a bound contribution, which is from the dipole, and in a free contribution that is then the Q I deal here with. But I mean, here I don't have the Q. Of course, it's
Thank you.
You're welcome. So that was very nice, but this, of course, doesn't mean that you can now always do single molecular strong coupling and you're fine. So it would be nice, but I think this is too easy. But should you ever submit a paper with few molecular strong coupling and get a referee telling you that this is completely unrealistic, then at least now we have an analytic example where we can say, okay, at least in certain cases, it's realistic, I would say. So this brings me a bit to another question, to temperature. So what we have just seen is now in specific cases, single molecular strong coupling results might be meaningful. And that's why here I have a single molecular strong coupling result. So what we could see, the details do not matter again, but what we could once solve was an HD plus molecule coupled to a single mode. So this is relatively easy. So because you have two different nuclei, we have and we have one electron only, and we have the photon mode. So these are all different type of particles. This problem we could numerically solve, of course, in basis set, whatever, or trying to convert it, but we could solve it numerically exactly. And if you have your numerical exact wave functions, the ground state and excited state, what you can then ask, what does temperature do? So you have your wave functions, and you can say, okay, I take my canonical ensemble density matrix and see what this canonical, so the temperature goes in here as, so this beta is the inverse temperature, and to get some understanding what temperature could do. And the main message here, or one of them I would like to give you, is this thermal ensemble here contains light and matter. So if your light and matter is in thermal equilibrium, this does not mean that only matter in there is in thermal equilibrium. So you can imagine, if you look now at the subsystem, for example, at the nucleus in there, and you trace out all from your full density matrix, you trace out all other degrees of freedom. So your nuclear subsystem will not have this canonical distribution. And this is important because there are quite some simulations out there. They then whatever do strong coupling, and you assume implicitly that your nucleus behave in canonical equilibrium, but that's only the full light and matter ensemble should be. And just to keep in mind, I mean, it's hard to investigate that, let's say, for more realistic system, but I think it's important to remember if your full system is in canonical equilibrium, it doesn't mean the subsystem, if they are strongly coupled, are in thermal equilibrium. Things change if your subsystem, for whatever reason, you can say they are only weakly coupled to the rest of your ensemble. That's what you then usually do. Yeah, how you basically argue the coupling to some, how do you say, weakly coupling to above argument, and then nothing interesting happens. But by definition, we should be in strong coupling, so you cannot, I would say, not a priori at least discard it. And something, when we did this simulation, something we noticed, the first thing was not so surprising. It makes just physically sense. What we looked at was because we had really the wave function, we looked at light matter entanglement in the ground state. And what we found, so this is temperature, we looked at the light matter entanglement at 0 temperature, you get entanglement, not so surprising. And then at some point it drops rapidly, and the entanglement is gone. If you do, this is a bit naive, but just to compare, if you do the same with the James Cummings, you create by entanglement by temperature. Makes not much sense. Of course, it does not, it's just to compare, but keep that in mind. But if the entanglement is gone, doesn't mean that all your quantum features are gone. It means just really So what we noticed is here, when we looked at the fluctuations in the system, you see here again, the temperature, they remain increased. So this would be, I think, the classical curve. And these, so this is then the electric field fluctuations in there. And this is a quantum feature. So what I want to tell you is that probably the coupling to the light, so here it's an all quantized setup, that you get some reminiscence of quantum features, probably even at room temperature of your, this we don't know. I mean, it's also just this example, many limitations, single molecular strong coupling, but still, I think this picture that probably you modify the fluctuations even at room temperature due to this, let's say, quantum fluctuations is also something to at least keep in mind too. But this needs more investigation, more, yeah, this is very ad hoc. Based on this very ad hoc picture, yeah.
So the fluctuation, these are quantum fluctuations, right?
Yeah, the point is exactly, I mean, at some point, if you increase the temperature, you will approach the classical limit. But this is quantum, this is a consequence of the quantum nature, yes.
But so it's expected that it goes up as I increase the temperature?
Yes, you increase the fluctuations if you increase temperature. You are more delocalized, you populate more delocalized orbitals and so on.
Do the thermal fluctuations act in the same way as the quantum fluctuations of a cavity?
That's a big question, I don't know. But that's, yeah. I mean, in certain, I will not address it in the seminar. I think there is a difference, actually. But in this picture we are looking here, I don't know what it means. Just to summarize a little bit what could be a picture, how to think about temperature in this strongly coupled ensemble. Of course, if you are at very low temperature, you get light and matter entangled in your ground state, or that's what you would expect, but you probably lose it very quickly in reality. In reality, probably even much sooner, I guess. And then you probably enter some regime where still the quantum nature of the fluctuations sort of influence your matter dynamics in one way or other, the details, I don't know. And then, as I just said, at some point, if you go to higher temperature, you should always sort of converge to the classical limit. And then here, if you, so this was the different coupling strength. So this should sort of apply, at least from our understanding, vibrational, raw vibrational regime. If you go to electronic strong coupling and then look at the vibrations of the nuclei, I don't have any clue. But it's interesting to ask if you want. Yeah. Yeah, I will, I think, I talk about it right now, I think. So, but what is sort of interesting is that this modified fluctuations, of course, at least change. So you're simply speaking here, you should not necessarily be in this classical canonical picture anymore, and that can have interesting consequences. I will talk later. How is the time? Do I have time? Check. Yeah, I skipped this slide. So the next thing, so far we discussed always this harmonic setup. It's all harmonic, it's illustrative, but of course reality is not so harmonic. So I do a minimal step further, I would say. I look now not at the harmonic 1D molecule, but I look at a so-called Shin-Matthew model. What it is, it can do many things, but it was originally, I think, designed for looking at chemical reactions. But you can imagine you have two fixed nuclei at a certain distance. You have a quantized electron. You can have a quantized nuclei that moves, but in our case, this is then classical. So we still have one electron per molecule, but the potential in here is not harmonic anymore. Of course, this I can only solve numerically. The first sanity check we did is how does, if you couple it to the cavity, how does the Rabi splitting scale with the number of molecules? And you see you get this square root of, so this is square root of n, it's a bit small. So you get what you expect from models from quantum optics. So this is, you get it locally, you get it collectively. So this is a sanity check. But, and this I think is sort of interesting. So we solved for that these cavity Hartree equations numerically, and at a certain collective coupling, we didn't, I must admit, we did not investigate it so carefully yet, but because it will have many implications. But at certain collective coupling, you get sort of degeneracies arising and you run into convergence issues. And this, it's important, so these degeneracies that arise, this is really some intermolecular issue, and this doesn't mean that your single molecules are degenerate. And so this is something we noticed, okay. Another thing that was then rather surprising is that when we looked at the polarization of a single molecule, so we did the dynamics of we did MD dynamics, and we looked at every time step, we calculated for the same, under the same condition, we calculated the electronic structure self-consistently with the cavity on and once without the cavity. And you expect that the cavity polarizes a little bit your molecules. It's not so surprising, you change a bit something, but it appears, I have also better graphs than this one, that this effect doesn't vanish in the large N limit. I mean, before in the harmonic case, I showed you that this Rabi splitting, that these local effects seem to vanish. And here it seems to converge to some, it's very noisy, actually. But this is probably also a feature, actually, not a bug. But you get something that at least appears for, we could do it up to 10,000 molecules, that seems to go to a finite local effect. But this effect is small. So this is not the end of the story for sure. But it seems like really solving the many molecules self-consistently is important. And we call it a polarization class. So what we notice is, so the total dipole of your ensemble that you induce quickly drops to 0. So you do not expect your ensemble to polarize, but you get locally, you get a polarization. So you can imagine you get sort of an anti-alignment of local polarization that cancel each other. So it's a bit the picture that we have, but it's a small effect. So this will not, at least to my understanding now, this is not the explanation of all the chemistry you have out there. Okay, a lot of red things. Okay. Oh, I have no summary slide. This brings me already to the, before the summary slide, to the topic of the seminar that is afterwards public. And you remember at the very beginning, I showed you these experiments with the two conformers. And what I wrote down is the London dispersion forces that are responsible for this. And London dispersion force are correlation, electron correlation effects. And I solved before we discussed Hartree equation, Hartree-Fock. Everything I showed you doesn't have electron correlations in there, so we need to go beyond. And that's then the topic of the seminar. And before doing that, I hope it's more or less understandable. I don't know. I tried to summarize a bit what I presented you in this lecture. So remember, we did this cavity-Born-Oppenheimer partitioning where we grouped nucleus and displacement field together. So we get two problems. We get this electronic problem, which is modified here by the cavity. And this is the simplest thing you can do with the nucleus. You say they are classical, and also the displacement field variables are classical, and they evolve on the ground state electronic structure that you get from this problem. Now, experiments are, I would say, almost always done under collective strong coupling, meaning you have a lot of molecules. And so this is a bit one starting point from a theory point of view that I tried to do. Then we looked mainly at dilute gas limit, meaning we say the electronic structure between the molecules does not overlap. But this was not easy enough, so we went to this very simple harmonic model. So we said all interactions in there are harmonic. You get only one electron per molecule and so on. And what we found from that is we could do vibrational strong coupling. You see that from the self-consistency that only higher active mode couple in the harmonic model, but you could also see that this local effect seemed to vanish in the large N limit, meaning if you do that, you would expect no, I would say no chemical changes under vibrational strong coupling. But you got a bit an understanding, hopefully, what's going on. But there was this one observable, this polarizability, where we could really see that for this observable, a local polarizability behaves as if the lambda is collectively increased. So at least you had this example where single molecular or whatever few molecular strong coupling makes sense. This was then the motivation to take short detour to discuss single molecular strong coupling at finite temperature. Here the main message was if your full system is strongly coupled in thermal equilibrium and you look at the subsystem, it doesn't mean that the subsystem is in thermal equilibrium, provided they are strongly coupled. And this we did not look at. And from this so what this didn't talk so much about that. This is important. So this single molecular changes that are collectively enhanced, this is a consequence of feedback mechanism. So that's why perturbation theory doesn't work. And that makes it computationally hard, you can imagine. So you somehow need to account basically all the ensemble of molecules then somehow are synchronized and can act together locally. And for that, you need to solve it self-consistently. And this then brings us to this polarization class I showed you, where we then go beyond the harmonic model. So we have unharmonicity, but we are still in the dilute limit. So these were these results. And now, of course, one can ask the question, this was dilute. We have no electron correlations, but we would like to go to liquids, for example, make it a bit more denser. And that brings me then to collective electron correlations, which will be the topic of the seminar soon. So I think, yeah, that's what it is. I don't have a thank you slide. Sorry, I forgot that. But thank you for listening. Questions? Yes.
So this collective coupling feature, so where the light matter coupling scales with the square root of number of particles, this is now in a single mode picture, right?
Yes.
Could you comment or maybe guess at what would happen if you would take into account the full mode spectrum of the cavity? Because
I would expect it behaves similar, but probably somewhat. Mark, do you have experience with this question?
I think it will depend a lot on the frequency spectrum of the other modes. So it has been seen also experimentally that in some cavities, if you are able to spectrally overlap many modes, so one way of doing it is you take your mirrors in the Fabry-Perot and you bend them so they are kind of around. Then in fact, the light matter coupling can, then you couple to many modes simultaneously, but from the perspective of your system within the long wavelength approximation, it looks like you're coupling to what some people call a super mode, and other people call a synthetic mode. And the light matter coupling of that mode can scale with the number of modes that you are able to overlap. So in principle, if you overlap them such that they generate in frequency, then the light matter coupling can scale up with the number of modes. If you have many different modes at different frequencies, then of course now you have a bunch of oscillators that can exchange energy with each other, and then it's less clear that you get scaling of the coupling strength, if that makes sense. But so yeah, so the answer is depends. But there are definitely cases where you.
I think what is one of the questions certainly is what is now N. So what is the space that now couples collectively under realistic conditions? It will for sure not be all the molecules you put in the cavity, definitely. And how this scale is also how to construct it. I mean, that's active research. Any other questions?
So, thanks for the nice talk. And I actually have two questions. One is that you calculated the local polarizability. So I wonder if you have any idea connected to the chemical reaction rates. Yes.
So I didn't think about that. One could try to do that. I don't know, to be honest. So yeah, we can do you have background on that? So we can discuss afterwards. No, I mean, one can now start, of course, to play around.
Yes. The other question is that as you show that the local properties gradually vanishes as n gradually increases. But that actually contradicts with the experimental observations. So I wonder if that could be because that the n estimated experimentally is actually not that large.
Now, Mr. Potter, what is not that large?
N is actually not that large that it can give rise to binary effects.
Yes, but I think so. What we usually, as my argument would see, what we usually put at least as a lambda parameter in these simulations is orders of magnitude larger than what you get in the experiments. So it's not. I mean, this is just. I would say this is a toy example where you see this local effect, but what happens then for, let's say, so this is also a driven setup in that sense. You put an electric field there. Now, what happens really in the dark, and how then you get the necessary local effects that are strong enough? I think this is not clear. And I agree. Yes, this model contradicts the experiments because we see an effect. I mean, you get chemical changes, obvious, if you're lucky. So if whatever you are on resonance, you are. Whenever you have the right chemical system, and this is not so clear yet. So I would say, yeah, this is the sort of the standard argument, this model, and it tells you locally nothing should happen. So the model, I would say, is wrong because reality tells us differently. Yeah. I don't know if this answers the question.
Yeah, maybe Dominik?
Yes.
If I just interject, but also because the limit is the wrong one, right? Because it's the dilute limit, all the experimental results.
Yeah, that's a good point. So, I mean, as a theoretician, it's very convenient to work in this dilute limit. And there are gas phase experiments where they see a Rabi splitting, but they did not report any other changes apart from that. And just from a theory point of view, also from looking a bit then at the seminar talk, I do not expect to ever get chemical changes in the gas. I mean, that's probably a bit too strong, but I do not expect to get chemical changes in the gas phase. Because I believe you need, it's a dispersion, electron correlation effects, and for that you need you cannot go, at least not in a theory, fully gas phase limit from a theory point of view.